Now TurboQuant, their new algorithm, is basically saying, hey, we've made it so that you can do less calculations with less GPU memory and still get the accuracy that you're looking for out of these models. OpenAI losing that deal and dropping the Sora project altogether, that was a very high level decision. That did not happen at the managerial level. That happened at the executive shareholder level, right? So what that shows me is they saw these other signals, which includes Google's newest research development.
TurboQuant, aka the real life Pied Piper.
Yeah, he likes calling it the Pied Piper because it's all about compression and doing shit faster. So let me just actually do a quick little, hopefully not too technical explanation of what this means. People are going to roast me about saying it this way, but this is the easiest way to conceptually understand it. Mathematically, this is not actually how this works. I just want to make that clear.
This is not financial advice.
Not financial or mathematical advice. Don't use this and go back to your math teacher and say, well, I heard this guy say, no. This is just a conceptual kind of exercise. So whenever you train a language model, the language model is basically doing these series of computations that are hundreds of billions of different calculations happening, and they all relate to each other. And the way I like to imagine it is basically like naturally, natively, the way that these work is that they round to the 1,000th decimal. Okay. So they go all the way out 1,000 decimal places on every single number so that they can have the highest accuracy possible. Right. So that's how the base model works. Like the base model does all of these very highly precise calculations hundreds of billions of times so that you can get the exact output of what you're looking for. Quantization is basically just rounding the decimal up. So instead of going to 1,000 decimal places, you go to 500 if you want to quantize it by a factor of 1. If you want to quantize it by a factor of 2, you go down to 250. If you want to quantize it by a factor of 4, you go down to, 100. So like each factor of quantization that you do, you're losing some of that accuracy because of the rounding, but the actual main point of the calculation itself is still accurate to within a certain degree, right? So what Google has done on their research side is create this new algorithm called TurboQuant that basically makes it so that you get the same benefits of rounding up, but you lose less accuracy in the rounding because they add a different layer to the actual calculation and storage of the numbers. So the reason that this matters so much is because at the heart of all of these models, vectors are really what's creating a lot of the prediction, right? So whenever a text goes into a language model, before they can actually predict what is going to be the output, they have to convert it into a vector, and then they use those vectors to do all these calculations on the inference. So with TurboQuant, it makes it so that instead of needing to have this huge data file that has hundreds of billions of numbers that go all the way out to, the 1,000th decimal, now you can just have this much, much smaller file or a few smaller files that don't have to run all at the same time. And you don't lose as much of the accuracy as you do when you just try to basically brute force the root or the roundup, I should say. So instead of just making assumptions and just allowing for dead space in the calculation, now TurboQuant, their new algorithm, is basically saying, hey, we've made it so that you can do less calculations with less GPU memory and still get the accuracy that you're looking for out of these models. So the reason that's kind of a big deal is because now the infrastructure that's needed to be able to get the highest performing AI models to run is much, much lower because you can run it all on a much, much smaller GPU with a lot less memory, and you can run it a lot faster. And so ultimately it's just more so an underlying improvement on how these AI models work.
Yeah, so they're saying like this will reduce the amount of working memory that an AI model would require by like a factor of 6, I believe, like somewhere in that range.
They have different versions, but yeah.
Yeah, so like you're going computer shopping and like trying to buy some fat big old Mac Studio, And using these numbers right here, you can literally like either shop 1/6 of the price you were going for, you know, or 1/6 of the size of the RAM, or have 6 times more power, essentially.
Well,
So
what
pretty cool.
I would also say to that is that's on the inference side, right? But
Yeah.
think about this on the training side, because the majority of the RAM that is actually being used in AI right now is actually on the training side. It's not on the inference side. Training is what requires way more calculation and requires way more RAM and just way more memory in general to be able to fit all the data that you need to be able to do the calculations. So I would expect Google to have a brand new series of models coming up that are run by this TurboQuant algorithm in the training process, because basically whenever you're building a language model, you're just kind of putting layers together that are stacking like different transformer encoders and decoders and vectorization calculation stuff. So when you are able to make the vector layer smaller and do it faster, the training itself can be done faster. So when you used to be able to run like 100 of these models at one time, like you said, because the memory space is improved by 6x, now you can run 600 of these models at the same time, right? So you get that 6x factor on the training side, and then what that allows you to do is evaluate those models all at the same time, and you get to pick the winners out of 600 rather than 100. So when your batch training size goes up by a factor of 6, you can assume that now you're going to get 6 times the number of winners from each, because that's all these training series, you know, really are, is they're just changing hyperparameters, like they're tuning some of the hyperparameters in the different layers of the model, and then they're just comparing how those differences do in the final output based on the benchmarks. So again, if you're training a full-size model and you have this crazy beefy, you know, NVIDIA GPU stack, you can probably train, let's say, 100 variants at the same time and then see which one did the best on the training performance. But if you can have 600 running at once, now you've got 6 times the number of winners that you can pick, and then you can take those kind of differences and then you can create the next 600 batches that you want to run, and your training process gets much faster. So this is really just going to accelerate the pace at which we're going to see new models coming out and new variations of models and improvements.